It's my pleasure to introduce Elke Visser, the speaker for the morning keynote, and his research interests are focused on declarative ways of defining and implementing programming languages. And if you heard something about such infrastructures and frameworks as SDF or Stratego or Spoofax, that's what he does. I think that's enough for the introduction. Elke, the stage is yours.
Thank you, Dimitri. Thanks for the invitation. Yeah, so before I start, let me ask you if you would be comfortable to do so to share your video, because then I have a bit of an audience in the talk today. It is rather weird to be talking to just my screen. So yeah, that would be great. And also, if you have questions, don't wait until the end, but just shout. I don't know whether you can unmute yourself. Dimitri, Jason, did you enable that?
I've got at least us open, and let me go see.
I believe I can talk also.
Now mute themselves.
Okay, excellent. Then, all right. So if you have questions, then please let me know, and I'll yeah, anything. We'll see. Okay. So my talk has. Well, I guess the organizers see a relation from my work to miniKanren, so I will not attempt to talk about that. But if you're welcome to bring up that relation. So I've titled this talk "Executing Declarative Language Definitions." So I'm Ilke Visser. I'm a professor at TU Delft, and there I work with a large team of students and postdocs, and have done for a long time on a project called Spoofex, which is a language workbench. And I'm going to talk about that. So let me start at the beginning. So if so this is all about language design and language implementation. And if you're a language designer, then well, you come up with some language design, some sketching on paper, and at some point you want to turn that into an implementation. And typically the first thing you do is to make a compiler or interpreter, so something that can execute your programs. But then if your language grows, you need more than that, right? You need an IDE typically is required these days. You may want to, if you have users, you may want to write some documentation, and those users may want to rely on your language, so you may want to prove some properties of your language. So there's quite a few artifacts that you need to produce if you're implementing a language, and if we look at those, then we see that those artifacts have a lot in common. Right, so you have all of them need some kind of syntax, maybe in different forms, but they need a static semantics or a type checker. You need to say something about the dynamic semantics or operational semantics, what it means, and it can be at a sort of a theoretical level. It's an operational semantics, but at the concrete level, you need to write a code generator or an interpreter, and so of course all these artifacts for these are aligned, should be aligned. But typically what you do is for each of the artifacts, you re-implement type checking or static semantics in a slightly different way. And so that is a lot of waste and a lot of cost for a language designer in order to turn a language design into a language implementation. So wouldn't it be nice if we just could write a language design and generate those artifacts from a single language design? Well, so people are working that in the area of language workbenches or language engineering. People have been working on tools like parser generators to generate tools from formal specifications. And on the other hand, and that's really aimed to generate tools, right, to produce working implementations. On the other hand, in the semantics engineering field, people are working on formalizing language definitions and proving things about the properties of languages. And there you have another set of formalisms to describe languages. So what I would like to see is a sort of a unified approach to this, where we specify a language design, so the syntax definition, static semantics, dynamic semantics, transformations, at a high level, and generate all these artifacts from such a language design. And so basically, that is my research agenda. And the way to achieve this is to use multi-purpose declarative meta languages. So meta languages are languages to describe languages. They're meta, right? They're about languages. They're declarative in the sense that they abstract from implementation concerns and they're high level. And they're multi-purpose. So you should be able to derive a parser, but also a syntax definition for a documentation. Right, so that's what I'm working on, and so here's a recipe for such declarative meta languages. So what you would like, so basically what makes a meta language multi-purpose is that you reuse the understanding of how to turn language aspects into tools, and rather than have a particular language designer come up with how to do code generation or how to do parsing. We make that into a reusable aspect that can be reused by language designers. So the idea for a meta language is to so the language designer uses the specification formalism to define language-specific rules, and then there is an underlying language-independent representation, and we have a declarative semantics, and that's what the language designer understands. So declarative semantics says, well, what is a model that satisfies the specification? And then we can have various interpretations for that declarative semantics to derive different kinds of tools. And these tools, right, so should be language independent. So we should be able to reuse the implementation for the meta language for different languages, so that language designers can focus on language design and not on tool implementation. And of course, these tools should be sound with respect to the declarative meta, the declarative semantics, and we can make different tools that are sound with respect to that semantics. All right, so that is an abstract story. So now let me make this more concrete and tell you about how we have been approaching this in the context of the Spoofex language workbench. So what is Spoofex? Spoofex is a tool. So it's things really. On the one hand, it's a tool for implementing programming languages. It's open source and it's freely available. We use it in education. It's used in research and in industry. And we spend a lot of effort in maintaining it, in engineering the tool. It's also so it's really a big software engineering project. At the same time, it's also a long-term research project. So it's an incubator for language engineering research. And it's the basis of implementation and evaluation of more than 100 papers. And also it's a sort of an imperfect approximation of the sort of the ideal that I sketched on the previous slides. We've been working on this for quite a while. So I started in the late 90s with Stratego XT, which was a command line processor based on SDF and Stratego. Then we switched to Java and Eclipse. So built IDEs on top of that stack. And Spoofex 2 has been a next generation where we have made that independent of Eclipse. So we can bind it to different IDE frameworks. And we've been developing more meta languages for static semantics and dynamic semantics. And this is what I will be talking about in this talk. In the meantime, we have started work on Spoofex 3, which is sort of the next generation where we is incremental from the bottom up, and so to enable live language development at all levels. So it's not just a research project. We use this for real. So we do research in language engineering and language prototyping. We use it in education. So next week I'm starting again with the compiler construction course in Delft. But before that, I need to grade the projects for the language engineering project, which was in Q4. And the students are waiting for their grades. So there in that project, students built languages in Spoofex. And we use it in academic flow engineering, so building tools to help colleagues deal with the the various workflows in research and academia, including researcher.org, which you know from the ICFP website. And WebLab is an online tool for program education where students program in the browser. And we have implemented these things with WebDiesel, which is a web programming language, which we have built with Spoofex. And it's also used in various projects with industry. And in fact, we're hiring PhD students in a new project on software restructuring. All right, so in Spoofex, we have multiple meta languages for language definition that address different aspects of language definition. So we do syntax definition with SDF3, static semantics with statics, we do data flow analysis with FlowSpec, transformation with Statigo. We are doing various experiments on dynamic semantics, and there's also a little language for configuring editor services. Today, I'll be illustrating how we instantiate this idea of declarative meta languages for syntax and static semantics. So I'll be talking about SDF3 and statics. All right. Any questions so far? I'm going to see if I can. Oh well. I used to be able to get rid of non-video sharing participants, but I don't see how to do this. Yeah. Anyway. All right, so let me talk about SDF3. So SDF3 is the name stands for syntax definition formalism, and it is the third generation in this language, and it is really a prime example of a declarative meta language. So it is declarative in the sense that as a user of SDF3, you don't have to understand the underlying parsing algorithm. You really can specify syntax rules, as we'll see, and it just works. And what you're thinking of is in terms of trees, the underlying structure that you assign to programs. And so that's the language independent structure that we see. And then in the formalism, you define constructors, productions, you use templates, as we'll see, and separate disambiguation rules to do disambiguation. This language has a declarative semantic, namely whether a syntax tree is well formed with respect to the syntax definition, and that it's easy to see. You can just see, well, yes, this is a correct tree with respect to the grammar. And that's all you need to understand as a user. And then the tools take care of operationalizing that. Of course, we get a parser from a SDF3 definition, but also formatting based on layout hints in the grammar, syntactic completion, and more. And we'll see that. So it's really a multi-purpose DSL. So the core of SDF is to define syntax as structure. So if we define grammar rules, so you're seeing my cursor, right? Not, yes. Yeah, so a grammar production has a non-terminal and a body, but it also has a constructor. So that's the name of the language construct, but also the constructor for the AST. And you really should think of these things in terms of the structure, right? So an expression is another expression, and a plus sign and another expression. And so there's this mapping, syntax definition, define a mapping from concrete syntax notation to trees or terms according to these constructor definitions. And that is the key reasoning you use as a user. And then you get all kinds of tools. For example, formatting. So here I've slightly changed the rules into so-called template rules. So here I'm quoting the body of the production, and so everything that is within these quotes is literal text, except if you use an anti-quotation, right? So you have an anti-quotation for exp. So that says here we're going to use an exp non-terminal. And these templates not only specify sort of the structure, the notation of the construct, but also how you want to pretty print it. So here we see that if you have a tree that is correct according to this grammar, you can format it using the layout hints in these templates as instructions for the format. So from these productions, we get both a parser, but also a pretty printer, and that is quite neat because that's often what you need when you're writing code generators, etc. And right, another interpretation that we provide is syntactic completion. So if you have programs that are incomplete, so you generate syntax for placeholders, right? So for every non-terminal, there's a corresponding placeholder in the syntax. Then what we do is generate a syntactic completion service that you can apply to these placeholders, and then you get a bunch of proposals based on the syntax rules for that non-terminal, right? And that's all, and that you get that automatically from based on the syntax definition. All right, then there's disambiguation. So if you've taken a good look at this, the syntax definition that I showed before, then you see that it is ambiguous. For example, this addition expression is left and right associative. So if we have two additions, right, A plus B plus C, then there's two ways to parse this. It's either A plus B plus C or A plus B plus C. And so what is disambiguation? So often that is interpreted as, well, now we have to rewrite the grammar to be unambiguous. Another view of disambiguation is, well, disambiguation is selecting a preferred tree from the set of possible trees, right? So here, if you say that I would like addition to be left associative, then you choose the second tree rather than the first tree. And this is implemented in SDF by providing separate disambiguation rules for the grammar, right? So here we are saying with this annotation that addition is left associative, and that application has higher priority than addition, has higher priority than everything else, etc. And declaratively, these disambiguation rules are interpreted as tree selection filters. So given all possible trees that you get from the ambiguous parts of a sentence, you use these priority rules and associativity rules to select the rule that you are interested in. Of course, you want a more efficient implementation where you implement these priorities in the parser, and so that you can only produce one possible tree. But that is not of no concern to the user. So conceptually, this is the model that you provide. And this includes things like dangling else, right? So here we have if then else. So we have an if and an if else that is ambiguous. And a typical way to disambiguate this is say, well, an if should belongs to or the else belongs to the closest if. Well, so one interpretation of disambiguation is during parsing, right, where you you make sure that you select the right parse tree. But another an advantage of having this as separate rules is to use these as parenthesization. So to insert parentheses when formatting. So, for example, when you you parse the expression over here, then in the abstract syntax, you're not interested in parentheses, so you can just leave this out. And if you're formatting, there's actually no need for these parentheses because addition is left associative. But if you have parentheses that are necessary, then you would like to reproduce those. For example, in this expression, no parentheses are necessary, but in this expression, you would like to reintroduce these parentheses. And again, we can automatically generate a correct parenthesization based on the disambiguation rules. So what we've seen is based on a single source definition of syntax definition, we get multiple tools. We get parsers with error recovery, we get pretty printers, we get an abstract syntax schema, we get syntax coloring, syntax completion, etc. So this is the sense I have in mind for multi-purpose languages. And you can see that here if you when you define syntax in SDF or in Spoofex, then what you do is write a grammar and you get a whole bunch of tools for free. And you can write programs and get a lot different tools out of them. All right, any questions so far?
I have a question.
Go ahead.
Actually, it's sort of a few of them. How far this approach of SDF can be scaled up? Is it possible to devise a parsers which say layout based? What about user-defined operators, infix operators, which use defined associativity and precedence like in Haskell and all
Right.
those? Can it handle these cases?
Right. So we do indeed have an extension of SDF with the layout sensitive, or it's built in. So we support layout sensitive syntax. So and that's where you mean Haskell-like offside rules or Python-like syntax, right? So based on so-called layout constraints, you can define that certain elements should be aligned, or that certain elements should be have an offside rule, right? So it should be to the right of the predecessor. We also do support. So we do support user-definable priority in the sense of Haskell NML. So I just implemented so Haskell and ML have different approaches to this. So I just implemented a syntax definition for ML, and I have a talk about that tomorrow in the OCaml workshop. So for OCaml, actually, I have to say. In OCaml, and I think also in Scala, the approach to user-defined operators is to have operator schemas with fixed priorities, right? So you say all operators starting with a star have higher priority than all operators starting with a plus, right? I mean, I think that both OCaml and Scala have that approach, and there you use directly the approach that I've shown here, but you just have a larger set of operators, right? So you say you have infix operators have the bin op 6 production, and the plus operators have the bin op 5, and then you define a priority rule, and it works out just as I showed here. For Haskell, it works slightly differently. There you can introduce user-defined operators on the fly, as I understand. But then what they do in the parser is use a fixed syntax for parsing operators, and then reorder trees afterwards according to the declared priorities, if I understand the approach correctly. Is that your understanding too, Dimitri?
Yeah, thank you.
Yep. So there's yet another approach where you truly have a truly dynamic extension of operators, like in ACDA or COC, and that is not so. There you really need a dynamically extensible parser, right? And that is not supported by SDF at the moment.
Yeah, I see. Thank you.
Other questions? All right. If there are no other questions about SDF, I will go on to the next chapter. So, which is static. So, for static semantics, we apply a similar declarative approach, and I'd like to talk about that. Right. All right. So again, we follow the same recipe. So we have a language independent representation for representing binding in programs, so-called scope graphs. We have a formalism in which users define language specific rules. So consisting of type constraints, scope graph constraints, and name resolution policies. We have a declarative semantics for that language, which defines how a scope graph satisfies the specification. And that is really not sort of an operational definition, but really a declarative definition. And then we have language independent tools based on this. In particular, so the one that is in sort of live in Spoofex is we derive type checkers from static definitions, but we are also working on refactoring, renaming, code completion, and more. Yeah, I could give a quick demo if I can find the. Share, right. So this is Spoofex, and it's so Spoofex is an Eclipse plugin, and here I'm showing the interface for the generated language, which has a syntactic definition in SDF, and it has a type checker, a type system definition in statics. And here you see that, well, you get various tools, you get code navigation, you get checking. So if I misspell well, let's misspell a different one, a use of a name, then I get an inline error, and etc. Right? So this is the kind of environment you get for from a language definition. Where is my there? Okay, so what is statics? Statics is a logic programming language, and I think that is a connection to miniKanren. And it's a pure logic programming language, so not in the sense of so there's no backtracking and there's no cuts. What you do in statics define predicates. So here we see a predicate that defines a predicate type of exp that takes a scope and an expression and produces a type. And it says, well, the type of this expression is this is the type of this expression. We can also have the predicates that define the well-formedness of constructs, like this declaration is okay, or these declarations are okay, etc. Yeah, if a predicate holds for a term, then the term has that property represented by the predicate, for example, type of exp, or type of type, or level of type. And the scopes represent names or name binding, as we'll see in a bit. So in statics, we have this functional notation that are somewhat isomorphic, but when you use the functional notation, it's a one-to-one mapping. We're saying this expression has one type. If you have the predicate notation, then an expression can have multiple types. So then we define predicates by means of rules. Of course, the predicate declaration should be type of exp here. So a rule has a head clause, it has a head, and it has premises, and it is universally quantified over the variables in the head. But this should be fairly familiar if you're familiar with logic programming languages. And then how do we interpret this as a type checker? So we take a program, we parse it with a syntax definition that gives us an AST that may give us parse errors that we then and syntax highlighting that we display in the editor. The syntax definition gives us a signature, and against that signature we have defined a type system rules. These are interpreted by the solver, so using the AST and the type system rules. And that gives us possibly type errors that then are displayed in the editor. So that's the basic idea of statics, and well, if you're familiar with logic programming, that is pretty standard. So what is interesting about statics is that it deals with name binding. It has a built-in notion of name binding. So if we wouldn't have names in programs, then type checking would be fairly easy. But names are a key problem in programming languages, right? So we have many kinds of name binding patterns. We have to deal with erroneous programs. Name resolution really complicates type checkers and compilers. And typically what we see is that they are treated in an ad hoc way in various tools. So is there a systematic uniform approach to name resolution? And that is what our work on scope graphs is about. So how does it work? We do take a program, we map it to a scope graph, which consists of scopes, which are regions in a program that behave uniformly with respect to name binding. We have declarations in program, declarations of names such as fact or n. Over here, these are declarations of names. Then we have references, right? So the reference of fact here and here are references. And then finally, we have name resolution, which is a matter of resolving paths in the scope graph, right? So finding a path from a reference of factorial over here to the declaration over here. And while the mapping from a program to a scope graph is language specific, resolution in the scope graph is language independent. So that's a reusable aspect of name binding that we can reuse across programming languages. All right, so how does that work? Let's look more closely at some examples. So here we have our language. So we start with simple definitions, declarations, and references. So in this language we have bindings that bind an expression to a variable, and it also declare that variable. And in these expressions, we have references to variables with the var constructor. And then we have a predicate that determines whether such a program is type correct or is correct. And that is defined by the Decl OK predicate. And so what? And we already saw the type of X predicate before, right? So in order to define the correctness of these programs, what we see here is well, so what is the type of a variable? Well, that's the type of var, right? So we need to look up the type of var. So we've defined a separate predicate for that. To check a binding, we use the bind OK predicate, which well, it checks the type of the expression E and comes up with some type T. So T here is a constraint variable. So we are doing type inference, right? So we're inferring the type of the declaration X by the type of the expression E. And then we want to register the fact that X has type T. And so we use another predicate for that, declare var, that says in the bound scope, variable X has type T. Okay, so that's pretty straightforward. But so we haven't done anything. So we have delegated all the magic to these type of var and declare var predicates. Let's have a look at those. Right. So what they do is they take a scope. That is the scope in which a variable is declared or bound. The name of the variable, and in the case of a variable, we provide a type. And in the case of a type of var, we want to find out the type of the variable. And then what we do is define a name resolution policy that consists of a namespace. So we want to maybe distinguish variables from modules or other kinds of names. So that's what the namespace is about. We have a resolution policy, which is for now just E, the empty policy. And we have a declaration relation that relates occurrences of names to types. All right, and then, well, we want to define these predicates. And what does that do? Well, declare var is defined as there's an edge from the scope S, so the binding scope, to the variable X with type T. And we see that in the scope graph picture over here, right? So that we see that A, B, and C have type T, have type int in this scope. And then we have a type of var, and type of var is defined using a query that says, well, starting in scope S, find a path to a declaration X prime, and which should have the same name as X, which is built into this query. And then, according to this type of Decl relation, which binds this type T to the variable, and that is the type that we're producing as the result of type of var. All clear, Michael? All right. Okay, so basically what we see is we resolve references to declarations according to these definitions. So how about shadowing? How about some more interesting binding structures? So let's look at lexical scope. So here we have a let binding, and that's well, a let binding has introduces a variable, the initializer expression, and the body of the let. And how we want to represent this is as a scope graph that says that from the inner scope we can see bindings in the outer scope. So how do we define the type of X predicate for let bindings? Well, we say, well, we want to find out what is the type of the initializer expression E1. And we do that in the current scope, right? So we want to find out what the type of this expression is in the scope before we define A. Then we introduce a new scope, aslet, and we introduce an edge in the scope graph from the new scope to the parent scope. And that says, well, from aslet we can see things in scope S, but not the other way around. Then in that new scope, we declare this new variable x with type S, so the type that we found from the initializer expression. And then we type check the body of the expression using this new scope. And then we define a resolution policy that says we can now traverse a number of p edges in order to find a declaration for the var namespace. Right, and this means that from this reference C, we find this declaration. From this declaration of B, we follow this path to find this declaration, etc. Any objections? There's a question on, so what sort of thing is aslet? Did you introduce a particular kind of first-class object, which is a lexical scope? Or did aslet have behaving Alexa? Just find out how you represent data in your logic programming language. Yeah, so aslet is a scope. So that is one of these circles. I mean, it is a special kind of thing, but the fact that it's a lexical scope is not baked in. Right, so the fact that the lexical scope is created by these edges. So I've said there's an edge from scope 2 to scope 1, and that means when I'm doing a query from B, I can follow this edge to find a declaration over here, and that is the notion of lexical scope that we're encoding here. But in a bit, we will see that we can encode other kinds of scoping. So module scopes using the same mechanism. Does that answer the question, Andy? All right. Okay, so I was asking for an objection. So let's let me object myself. So if you now change the example a bit and have two definitions with the same name, then both names might be reachable with the policy that I showed on the previous slides. So what we do add is to define lexical scoping is this path specificity notion, or the visibility notion, that says, well, there are multiple paths from this reference, right? So from this reference we can reach this declaration, but also this declaration. But using this path specificity order, we can filter those paths, and in this case say, well, we prefer a path, basically a shorter path over a longer path. And that's right. So the edges that show nesting, that represent nesting of scopes, together with this notion of path specificity, formalizes lexical scoping. But that is just one policy that we can formalize in statics. All right, so in order to see that, let's look at non-lexical bindings. So there was a discussion on the types list, and so these things I call lexical bindings, right? So lexical bindings are characterized by nested scopes, and you can find references by going up scopes, and they correspond to sort of a domination structure in the program. Non-lexical bindings are things like modules, and where we find references in sibling scopes, as we'll see here. So here we see, so this language has modules, named modules, and you can import modules into other modules, and it means all the things you've defined in that module are also visible in a module that you are importing it into. And how do we represent that with scope graphs? Well, here we see the basic structure, right? So these modules are represented by their own scope. The module names are linked to a scope as a type. So mod1 so the type of module A is a scope that refers to the scope, so the container of things, of the things of A. And in this structure, we cannot see, we can only see the things in that module. Now, in order to implement imports, what we do is, so an import, right, module names are just names in this scheme, and an import refers to a name. So what we do to resolve an import is first we resolve the name B in the scope of the A module. That resolves to this name B, and that name has a type, and that is the associated type of that name, and it happens to be a module. And so what we see here, if we look at a module, then if we find the type of a module, then what we do is we create an edge from S, the importing module, to smod, the imported module. Right, so here we get an I edge from the module that imports module B to the scope that represents module B. Now, given this new edge, we can then resolve through import edges, right? So the C over here can now be resolved to a module in this in the module over here. And now there can be multiple edges, right? So for example, if we have a variable B over here that is defined both at the top level and in this module B over here, then both these may be reachable, but we may want to have define a policy that says, well, we prefer imports over lexical parents. So in this policy, we say that I is less than P, so that means we imports shadow variables visible from the lexical context. And so, and for example, here we see a modules with mutual imports, right? So A imports B and B imports A, and it is just as easy to achieve with this schema as before, right? We resolve B to this scope or this name, and it means we create this I edge, and we resolve A to that module, and so we create this I edge, and so we can resolve in both directions without difficult problems. So the resolution policy takes care of cycle detection and so on. And another thing is transitive imports, for example, right? Where we not everyone likes this, but suppose you have a language with transitive imports, right? You import in module A, you import B, which imports C, and so from module A, you want to be able to see the definition in C. Well, that's just a matter of creating these I edges and then resolving along these I edges to find the definition of a variable C all the way in module C. All right, I'm actually finishing on time. That's good for a change. All right, so this is the basic idea of statics. We define, it's a logic programming language that has scope graphs as a sort of domain-specific extension, where we, as part of solving a predicate, we build up a scope graph and resolve questions in that scope graph. And it's important that happens in a safe way. So, for example, imagine that you are in this mutually recursive situation. If you would try to resolve resolving a reference before you do the imports, then you get the wrong result. So statics guarantees that it finds a proper schedule and only resolves queries when it's sure that all information is available. So I've shown these notions a bit in an operational style, right, where we construct the scope graph as we solve. But really, the declarative view is that you should interpret these rules as there is a complete scope graph for the program, and then you see whether the predicates hold in that model. The operational interpretation of actually building that scope graph is one of the interpretations of statics. Right. So there are multiple interpretations, just as with SDF, there are multiple interpretations for statics. So the default interpretation is first of all, it has a declarative semantic. So given a scope graph, a complete scope graph G, does a program P satisfy that specification? And then there's various interpretations, right? So type checking, we interpret statics as a type checker. So given a program P, build up a scope graph that makes the specifications satisfy. And in a recent paper, we showed that operational semantics is safe with respect to the declarative semantics. And we're working on other interpretations are like, well, can we concurrently or incrementally execute these specifications in order to incrementally type check programs? But there are other interpretations. So at eCoop last year, we had a paper where we explore code completion. So that's still work in progress in Spoofex. But the idea is, well, given an incomplete program, as I showed before, right? So a program with holes, what are valid completions for that hole? And it can be, well, what name can I use here, but also what kind of context constructs can I use here that are type correct. Other things we're working on is safe renaming, right? So and language independent renaming. So that's, I should stress that. So given a static specification, you get a code completer or a renamer. So can I change the name X to name Y, and is that safe, right? So it will not lead to name capture. Other things that we can work on is quick fixes. So suppose there is an error in this program, what are possible repairs for that error? And random term generation is, well, given nothing, just, well, a placeholder, what are correct programs that to fill in this program? That is useful for testing all kinds of tools, or for fuzzing compilers, etc. All right, so let me conclude. So I've sketched a perspective of high-level declarative language definition, where we only make language definitions and derive a bunch of tools from them, given that we have multi-purpose declarative meta-languages. I've shown how we are working on the association of that in the context of syntax and static semantics. We are also working on exploring approaches to dynamic semantics. So can we derive interpreters or compilers from a dynamic semantic specification? And we have explored that in various contexts already. But we haven't reached the... So things like, can we optimize interpreters using partial evaluation? Can we show type soundness of an interpreter with respect to static semantics? So we have done work on intrinsically typed definitional interpreters. And we're working on, so we have tools for doing program transformation, but we're also working on making those, including those with name binding, for example. All right, if you want more information there, have a look at my my publication page. There's a lot more information there, and at the Spoofex page at the Metawork website. Thank you.